So today and the next lecture, these next two lectures, I'm going to introduce a different approach to topological conjugacy. And I promised you three techniques. We've done the technique of fundamental domains in various settings, one-dimensional, higher dimensional. Okay. And this one is going to be a different technique that's very interesting. And the setting in which we're going to introduce this technique is that of local let me call it local linearization. So let me first explain what we mean by local. So suppose we have two systems, as usual. Ideally, we'd like to analyze whether they're topologically conjugate. Maybe they are, maybe they're not, maybe we cannot do it, okay? So let's reduce the question a little bit and suppose we have two fixed points. We have a fixed point here and a fixed point here. So we have f of p equals p, and here we have g of q equals q. And the question is, can we find a conjugacy just locally? Maybe not for the whole system, but can we find two neighborhoods u, a neighborhood u, u of p, let me call this u of p, and another neighborhood u of q, and a conjugacy h, which at least works in this neighborhood. Okay, so this is a kind of a local conjugacy. At least it's something. Right? Now we have to be a little bit careful because UP and UQ are not necessarily invariant. So it could be, so remember, what does the conjugacy say? Conjugacy says that if you take a point x, and this point here is y equals h of x, right? And then we take the image of x, f of x, and this should map to the image of y. So h of x should be equal to g of y, which is g of h of x, right? So we're looking for a conjugacy that says that h composed with f equals g composed with h. This is the conjugacy, right? However, it could be that this point x maps outside UP, because we don't know what happens. All we know is that there's a fixed point here, okay? So it's okay, we just change the definition a little bit. Because this has a fixed point, P, then it cannot be that every point in UP maps outside UP, right? For example, the fixed point stays inside. And obviously, if these maps are continuous, then points sufficiently close to P will stay close, so they will also map inside. Okay? So there will be some region here. This will be f of UP. Okay? So these points here, the points, so if you intersect UP with f of UP, you will get these points, and the pre-image of these points will be some subset of UP. So let's say UP tilde, UP tilde is equal to the set of points x in UP, such that f of x is also in UP. Okay, alternatively, you can write this as UP intersection f minus 1 of UP. Okay, so these are the points that stay in here. And you have the same thing here, right? So really, this conjugacy, so let me give the definition. So the only points for which we can, for this conjugacy can be defined is clearly these points here. Okay, so definition we say that fixed points that F and G are locally topologically conjugate at P in X and Q in Y if there exists neighborhoods UP of P and UQ of Q, and a homeomorphism H from UP to UQ such that H composed with F is equal to G composed with H on U tilde P, right? On U tilde P. This is the set of points. So this set here, just the set of points X which stay inside the neighborhood.
Do you mean UP to UQ?
Sorry?
H from UP
Yes.
to UQ.
Yes, thank you. Okay, so this observation is just a little technical thing to be formally correct, okay? Morally, this is just saying that there's a neighborhood of X in which if as long as the point stays in the neighborhood, so because this neighborhood is not necessarily invariant, then this conjugacy only makes sense for points that's as long as points stay in this neighborhood. There might be points that stay in this neighborhood forever, in which case their images will stay in this neighborhood forever, and you have this conjugacy. If there's a point that only stays for 100 iterates in here, okay, then there's a corresponding point here that stays 100 iterates in here, and the conjugacy maps those 100 iterates to these 100 iterates, okay? So it's just a finite time, in some sense, conjugacy, okay? But it still means that you're matching up all the orbits in here. Okay, so so what kind of result are we going to have in this? So let me state the specific setting. So let's suppose now that we have our map. Let's suppose now that we have the specific case that F is a map from Rn to Rn, is a C1 diffeomorphism.
Sorry, from Rn to Rn or?
To Rn to Rn, yes. Okay, and suppose we have a fixed point. Okay, so here we have a fixed point, P. Now, do you know what the derivative, the differential of a map from Rn to Rn is, right? So the derivative at P, what is the derivative at P?
Linear transformation.
Is a linear transformation, exactly, okay? So let df, df of P is an n by n matrix, right? Which is a linear transformation. So this map is itself a linear map. Okay, so this is also a map from Rn to Rn. Yes? Now this map has a fixed point. What is the fixed point of this map? 0. Okay, so here we have 0 is the fixed point. So f dfp, this is the map of 0 equals 0. definition. Let me write here. So P is locally linearizable F is locally linearizable at P at the fixed point P if how did I say? If F and dF of P are locally topologically conjugate at 0 at P and 0. So the two fixed points. In other words, suppose that there is some neighborhood here, okay, UP, and some neighborhood here for the linear map. This is U, Q, U0. Let's say this is the fixed point at 0. Okay, such that these are locally topologically conjugate. It's just a specific example of this. Okay, it's exactly the same, except that now I'm interested in whether there's a relation between the dynamics in a neighborhood of the point P and the dynamics of the linear map, which is given by the derivative of the point P. Another way of seeing this, remember that I mentioned at some point in the one-dimensional case how if we go from information at one point, we're able to deduce information about the dynamics in the neighborhood of that point, right? If this is true, then that's what we're doing, right? Because we have information about the fact that P is a fixed point, and then we have some information about the derivative, right? And what we're saying is that the dynamics in the neighborhood of the point P is determined by the dynamics, by the derivative, by the dynamics of the derivative. Okay? So think of the two-dimensional setting. What would this imply? We looked at various linear maps. Okay, you remember we did a kind of classification of linear maps. So for example, one of the possibilities in the linear maps is that we have a saddle point, for example, right? So we have a saddle point. If you remember, what does the saddle point look like? A saddle point has these two eigenspaces, right? For example, depending on the various possibilities for the linear map, we might have a contracting eigenspace here, we might have an expanding eigenspace here, and you remember what that means about all the orbits is that they lie on these curves. We have curves going like this, we have curves going like this, and like this. Remember, this is the linear map, linear picture, okay? So what does it mean that you have a local topological conjugacy? What is going to be the picture in UP in this case? So we know that 0 needs to map to P, right? And then we know that there should be a homomorphism between H and P. So this homomorphism is going to send these curves to curves here, right? And these curves have a dynamical meaning because we know, for example, that if you take a point here, then what is the omega limit set of this point? Is 0, right? Because it's on the eigenspace. So there must be another corresponding curve here, which could do like this, but all these points, they converge to the fixed point P. The omega limit set is P because the conjugacy has to preserve the conjugacy. And then we have some other curve like this, okay, which is expanding, which means that the alpha limit set, right? So these have the properties that in backward time they converge to 0, and this has the same properties. So here, all the points in backward time they converge to this, okay? And similarly, also it needs to send orbits to orbits. So if you have these points that lie on this curve, you will get a similar picture. Okay, so what this means is that you have in this neighborhood, if this is true, if we can get this local linearization, it's called local linearization because we're saying that locally it looks like a version of the linear map. It's a nonlinear version, but it has the same topological structure as the linear map. So we get a picture of the dynamics in a neighborhood of the point P, which is absolutely non-trivial. In principle, you just have your diffeomorphism, you have a fixed point P. Who knows what happens for points near this fixed point P? Nobody knows, okay? If we can show something like this, then remarkably it says that the linear case is a model of this case, okay? In some sense, this is the philosophy. When you first study derivatives, you think of derivatives as a kind of approximation of your function, a linear approximation of your function. I know sometimes maybe you will have been read or been presented it like this, and in some sense we're implementing this philosophy that if you take a small enough neighborhood, then the linear map is an approximation of this diffeomorphism at P, and therefore the dynamics should be the same in this neighborhood. So the question, of course, is do we have this property? And so the theorem so let me say, give another definition. Say a linear map A from Rn to Rn is hyperbolic if none of its eigenvalues lie on the unit circle. This is a generalization of hyperbolicity of fixed points in one dimension. Do you remember? Do these two definitions match? Yes? So in one dimension, remember, hyperbolicity was that the derivative is different from 1 or minus 1. Okay? Because that was just real. So this corresponds. 1 and minus 1 lie on the unit circle. This is a more general version. In this case, the eigenvalues may be real or complex. If they're real, then it coincides with saying that it's not 1 or minus 1. If they're complex, they just need not to lie on the unit circle. Okay? And so these, all the examples that we did in 2 dimensions were precisely those ones that have hyperbolic. And then we say that fixed points, yes, so this is for the linear map, which is the derivative, and then if f is a C1 diffeom, okay, then a fixed point P is hyperbolic if derivative df of P is hyperbolic. So you have a fixed point, you look at the derivative df of P, that's a linear map. You check if this linear map is hyperbolic, then you say that a fixed point is hyperbolic. Okay, so theorem. This is really a fundamental theorem in dynamics. It was proved more or less simultaneously by both a Russian, Grobman, and an American mathematician in the 1960s, separately. And the theorem is that if P is a hyperbolic fixed point, then f is locally linearizable at P. Okay, so this is a very powerful theorem. It says that this holds every time that the fixed point is hyperbolic. Now, it may not hold, it may hold also if it's not hyperbolic, but you should know also already from the one-dimensional case, obviously why it cannot always hold if it's not hyperbolic. How can we show in the one-dimensional setting that this theorem cannot be true if P is not hyperbolic? What happens in the one-dimensional case?
The derivative is fine.
Exactly. So, yes. So what's the dynamics of the derivative as a linear map? What does it mean? If the derivative is 1, so in the one-dimensional case, we don't usually think of the derivative as a linear map because it's just a scalar, but the scalar defines a linear map, right? Which is just a map x goes to lambda x. So if the derivative is 1, then what is the linear map corresponding to it?
The diagonal y equal x.
Is the identity, right? Is the linear map is the identity. But as we have seen, we can have a fixed point with derivative 1, which in neighborhood is not the identity, right? It may be attracting, contracting, repelling, you know, there's all these various cases, okay? So if the derivative is equal to 1, then in that case, in the one-dimensional map, you can see that you cannot have local linearization in general. You might have the identity map, and then you have local linearization, but you have cases in which the derivative is 1, but the fixed point is attracting, for example, is attracting, but the linearization is the identity, so they're not conjugate. Okay, so hyperbolicity is a kind of a necessary. Well, at least you cannot relax it completely. Okay, there might be some special cases, like in those cases, you know, there might be some special cases, but not always, not necessarily. So we're going to prove a partial version of this theorem. We could prove this whole theorem, but the hyperbolic case is going to be a little bit. Is not so easy, but I can introduce all the techniques that we need in the special case in which this hyperbolic fixed point is an attracting fixed point. Okay, so we're going to prove this theorem, but when all the eigenvalues lie inside the unit circle, okay, so when you have an attracting fixed point. So that's what we're going to do. So let me just write this down. So we will prove this in the special case in which P, in which all eigenvalues of df of P are inside the unit circle. And actually the general case is not that much more difficult. So it's really the same techniques but adapted, and you introduce a few more technicalities that I don't want to spend time doing. So before we start, let me just make one more comment. Of course, you can use this theorem to study the topological, local topological conjugacy between two nonlinear maps, right? So if you have here F, okay, Rn to Rn, again the same setting that we had before. This is a point Q, right? And you want to know if there exists local topological conjugacy here, how would you use this theorem?
To go to the derivative.
Exactly. Exactly, right? So in this case, if you look now here, we have the derivative map here, and here we have the derivative map of G in Q, okay? And we know how to analyze the conjugacy between the linear maps. right? The linear maps with the method of fundamental domains we can study because we did it in 2 dimensions, but it all works in higher dimensions. So basically, it just depends on whether the eigenvalues, they have the same number of positive, negative, complex eigenvalues, and so on. So if these two are topologically conjugate, and this is if these 2 points are hyperbolic, and the 2 linear maps are topologically conjugate, then you construct a topological conjugacy here just by composing these conjugacies like this. Okay, so this theorem goes beyond, it's very interesting as a local linearization, but in some sense its main corollary is this, is that if two hyperbolic fixed points have the same, the derivatives have the same eigenvalues, then the 2 in the neighborhood of the nonlinear maps, they're topologically conjugate. Okay. So how do we prove this local linearization? So the fundamental theorem is the following, and we're going to state a theorem in a lot of generality, and we will really need to do that, which I'll see why. So the setting, we're going to have a very general setting, which is D is a Banach space. So you know what a Banach space is? Yeah. It's what? Complete metal space, vector space. Vector space, yes? Complete vector space, which may be infinite dimension. Euclidean space are examples, finite dimensional examples of Banach space. Right? Just normal Rn is a particular case. Okay, but there are many other spaces. Now, if we have a linear map, T, since it's a vector space, we can define linear maps. Okay, in this case, we do not define it as a matrix, but just as a linear transformation. You can define the concept of a linear map. Right? It has the property, it's linear, so T of x plus T of y equals T of x plus y, it's linear. Okay? Now we can define the norm of this linear transformation, so the Banach space has a norm. Okay? And we define the norm of this linear map in terms of the norm of the Banach space is equal to supremum of TV over V, right? For all non-zero vectors. So the image I at least have in mind is just a finite dimensional image. Okay, I know you know this, but I just want to make a comment. So if you think in 2 dimensions, right, you can take, by linearity, it's enough to take, for example, all vectors of V1. You could also define this as just TV where the vectors have norm 1. So you take the unit circle. What is the image of the unit circle under the linear map? We said the other day, it's an ellipse, right? So it's an ellipse like this, okay? And the norm is given by this distance here. Right? This is the norm of T. It's the biggest expansion. So there is some unit vector which is mapped to this, and that is the norm Okay? There is also a name for this. This is sometimes called a conorm. It's not exactly a norm, but this, if you think about it, it is, okay, I will let you think about it as an exercise, but this length here is exactly the inverse of the norm of the inverse. This length here. Because if you think when you take the inverse, then that means that this needs to expand to length 1, which means that if you take the inverse, a vector in this direction of length 1 will expand to exactly 1 over this t. Okay, I will let you think about it, but just a little bit of thinking will make you realize that this length here is exactly given by this. So in general, if you have higher dimensions, then this gives you the unit vector that is most expanded, and this gives you the unit vector which is least expanded or most contracted. Okay? So if you have higher dimensions, you have an ellipsoid that has many axes, right? And this one gives you the biggest one, and this one gives you the smallest one. So it's useful to keep this in mind. But this is because this is going to appear also in what we do. Okay, this is the least expanded direction. So the theorem is the following. So we're in this setting. So sorry. So we will say that T is a contraction if the norm of T is strictly less than 1. So that means that this ellipse is mapped strictly inside the circle. So that means that every vector is contracted. Right? So that clearly means it's a contraction. It's a linear contraction. So theorem. Okay, so T from E to E is a linear contraction, invertible. Linear contraction. How can a linear contraction not be invertible? What would it mean if it was
do for the 0?
Exactly. So you might have one eigenvalue equal to 0. Okay, if you think in one-dimensional case, that just means that there's a kernel, there's some of the eigenspaces they just map to 0. Right? So in other words, there's no eigenvalue equal to 0 basically. But in the infinite dimensional, it's not safe to talk about eigenvalues. Things are a little bit different. So that's why we just call it an invertible linear contraction. And suppose F is equal to, so we have a map F from E to E is of the form F equals T plus delta F. With delta F bounded and Lipschitz, and the Lipschitz constant of delta F is less than or equal to the minimum between T minus 1 minus 1 and one minus T. Is this number bigger or smaller than 1?
Contraction.
This is less than 1. Okay, because we've assumed T is an invertible linear contraction, so the norm of T is less than 1. So this is 1 minus something. And this is also less than 1 because this is actually the smallest contracted. So this in particular is also less than 1. Okay? So this is saying that Lipschitz constant is small. So we are kind of taking, in some sense, a perturbation, right? So we're saying that we have this map F is given by a linear map plus a Lipschitz map, which has small Lipschitz constant, or sufficiently small in terms of the properties of the linear map. Okay, then
This Lipschitz of delta of f means that the Lipschitz constant corresponding to this function? Or?
yes. So delta f is a Lipschitz bounded function. Okay, bounded means that the image of E is bounded in E. Okay, so it takes all of the space and it maps it to a bounded set of E. Of course, F is not bounded. Okay, what it means is you take F, you apply to some point of E, and what you get is simply the image under T plus the image under delta F. It's just a perturbation. It's like, think of it as a small perturbation of the linear map. So then F and T are topologically conjugate. In fact, we have a little bit additional information about the conjugacy. Remember, F and T are topologically conjugates. Conjugate means there's a homeomorphism between the two. And so more specifically, there exists a unique homeomorphism of the form H equals the identity of E plus delta H with delta H bounded, okay, such that H is a topological conjugacy. So this is just a little technical bit. In other words, we're going to show that the topological conjugacy is of this form, and in some sense this is saying that it's close to the identity. So this topological, so delta F is in some sense a small perturbation of T, and our conclusion is not only that the topological conjugate, but the topologically conjugate by the map that is just a kind of a small perturbation of the identity. So I think what I want to do today is explore a little bit the consequence of this, and then the next lecture we will prove this theorem completely. It's an interesting proof, and as I said, it's a new technique. We're going to use a different strategy for constructing the conjugacy. Again, as in the other settings, what we will need to do is construct the conjugacy. So we will need to literally, find or prove the existence of such a conjugacy. But what I want to do for the rest of today is think a little bit about what we're going to, in particular, how we're going to use this theorem to prove the Grobman-Hartman theorem, okay, in the case of contractions. So why is this theorem useful? So let's
require that delta H itself to be also Lipschitz.
This is not a requirement. This is just a conclusion, right?
Yeah.
So
a conclusion.
Do you mean whether we show that delta H is Lipschitz? I cannot remember. We might see in the proof. Maybe delta H will. I don't know. I cannot remember. We'll see in the proof. Okay. I think probably not, because I think the conjugacy, for the conjugacies to be Lipschitz, is all. That would mean that the conjugacy is Lipschitz. Okay, and that is almost like saying that the conjugacy is differentiable. It's very strong, It kind of means that the derivative needs to be the same. I'm not sure. I don't think so. Okay, we will keep that in mind. It's a good question, but I don't think so. It makes it more. It's a much stronger. Lipschitz conjugates is a relatively strong conclusion. Okay, so how do we use this for the Grobman-Hartmann theorem? So what the Grobman-Hartmann theorem in the contracting case is this, right? So Grobman-Hartmann wait, sorry, let me see. So we want to, okay, yes, so proof of Grobman-Hartmann when all eigenvalues are inside unit circle. So we're going to split it into two propositions. So how do we? So we're going to split it into two propositions. Let me write this proposition first. Proposition 1 is that if A is a linear map with all eigenvalues, with all eigenvalues in the unit circle. Okay, then there exists a norm on Rn.
The unit circle, you mean inside the unit circle? Or
sorry?
in the unit circle?
Inside, yes. There exists a norm on Rn such that in this norm, this map is a contraction. So why is it not automatically a contraction if all the eigenvalues are inside the unit circle? Why do we need to change the norm? So we have the standard Euclidean norm in Rn, or we have a given norm in Rn. And what I'm saying is that this becomes a contraction in a different norm. Why is it not necessarily a contraction already?
Because maybe the norms with that norm, the Euclidean is not.
Sorry?
It's not equivalent.
No, the norms are equivalent.
To the
Every norm in
Euclidean
Rn is equivalent.
So then Euclidean.
But why? So contraction means contraction, right? That every 2 points they come close. Remember, I gave you some examples in 2 dimensions already. I said, what does a linear map that has an attracting fixed point may not look contracting?
Because they are open. No.
Remember? So if, for example, if it has 2 complex eigenvalues, it may look like this. That is not contracting. because you have 2 points here and here, and they may map to this and this. The distance may increase. Okay, even in the case in which they have real eigenvalues, if you have, now I'm not sure how to do, so this is contracting faster than this, and then you will have these points maybe look like, they look something like this, I think. Okay, anyway, you might have points that if you take the unit circle, it does not necessarily map inside itself, just because the eigenvalues have less than 1. Okay, this is what I mentioned. This is something that sometimes we lose. When you study linear maps, you always look at the diagonal form, right, or the canonical form. In this case, the canonical form is the one where you are going monotonically inside, and in this case, the diagonal form is the case in which you do something like this. Right? And in these cases, if the eigenvalues are all less than 1, then it's actually contracting. Okay? But for a general linear map, the fact that if you take the eigenvalues have all less than 1, the fact that that implies that the fixed point is attracting is a non-trivial thing. Remember, I emphasized that when we looked at the case. It comes now from our knowledge of the topological conjugacy, or even the linear conjugacy of the linear maps, right? You know that these two maps are linearly conjugate, and therefore here you know that this converges to 0, and therefore here also everything converges to 0. But if you just look at this linear map and you look at the image of a circle, it will look like this. And then how do you know if in fact it's not a saddle? Maybe it's a saddle point, right? Where this maps to a saddle point like this. If you just look at the circle that maps to an ellipse, you don't know what happens. Okay? So it is not immediately, just because all eigenvalues are inside the unit circle, it does not mean that the map is contracting. Okay? But what this claims is, first of all, that there is always a norm that is contracting. This is actually, I will do the calculation here of the construction of this norm, but intuitively it's very simple. It's basically a version of the fact that you have this linear conjugacy to the canonical form, or to the diagonal form. It's essentially that. Okay? So this is the first proposition, and then now we have a contracting linear map. And then, now what are we going to do with this contracting linear map? Then we have okay, so proposition 2. Now we have A R to Rn is a contracting linear map. And suppose we have F from Rn to Rn, okay, where F is equal to A plus delta F, and delta F of 0 equals 0. And there exists a neighborhood of n of 0 such that the Lipschitz constant of delta f restricted to this neighborhood is less than or equal to the minimum between a minus 1 and 1 minus a. Okay, then A and F are locally, topologically conjugate, okay, at 0. So how do we get proposition 2 from this theorem here? Let's take a little break, 2-minute break, okay? Because I would like to just recover concentration. So let's. So what I want to finish now with the last half an hour to discuss the proof of these two propositions and how these two propositions imply the proof of the Grobman-Hartmann in this case. Okay. So this one I will do the calculation in a moment, but this one is quite easy. So what is the difference between the? This is a concept. This is a simple corollary of this main theorem. Okay. So that's why the proof depends essentially. This is the fundamental theorem. So what is the difference between those two theorems? Well, the difference is that here we are supposing that this is true in a neighborhood. Okay? If this was true in the whole space, then we would have exactly the result of that theorem. Okay? That's what. So the difference is that we're assuming this condition only in a neighborhood. Okay? But, you know, that's not a problem because we can now define a new map, f hat, that coincides with f in this neighborhood, and that continues to satisfy this assumption everywhere else. So we can kind of cut it off. So let me make this, let me write this here. Because this is short, we'll start with proposition 2. So, proof proposition 2. Let f hat from Rn to Rn such that f hat restricted to this neighborhood n is equal to f restricted to this neighborhood n. Okay, and Lipschitz and okay, we can write and f hat is also equal to a plus delta f hat. Okay, with delta f hat with Lipschitz delta f hat is equal to is less than equal to the minimum.
But how is if hat defined outside n?
We can define it in any way because we're just saying, okay, we have a map. So this is the map on the whole of our n, right? This is some neighborhood n, okay? So we know that f, so f is defined on all of our n. And f hat is also defined on our n. So this is given, f is given. So f on n will have a certain structure, okay? And it satisfies those Lipschitz derivative bounds. And then we can just define f. I mean, what does this Lipschitz bound? It just means, for example, if you take, so maybe we can define it to be, how do we do it explicitly? So, outside here, so what can be the problem? The problem is that this Lipschitz constant of f, so f is also of this form, a plus delta f. So f is equal to a plus delta f, right? And the problem is that the Lipschitz constant of delta f might blow up. So the derivative might be increased. So all you need is to write f of hat equal to f here, and then outside you just define delta f hat outside to be some function that has a small Lipschitz constant. So delta f can be 0 outside even. Delta f hat. Or constant.
But map here doesn't mean continuous.
Sorry?
Map here means continuous.
Because the Lipschitz, because it's...
I mean f hat is map, so it's continuous or it's just
Yes, of course, because it's a linear map plus a Lipschitz continuous map. Okay, so it's continuous. You do not need to define it as instantly 0 outside, but you can, you know, you have your map f hat. I don't want to try to write it exactly formally now because I might, but it shouldn't be difficult to do. You define f hat to be equal to f, then you take a slightly bigger neighborhood, right? And then you make sure that this delta f is 0 outside this neighborhood, it's equal to f in this neighborhood, and then in between the two, it's kind of just transitioning between one and the other. So it's quite easy to extend it with something that maintains the same Lipschitz bound, right? And then now you apply the theorem. So by the theorem, we have that A, and f hat are topologically conjugate, right? On all of Rn, on all of Rn. Okay, so we have f hat is now defined on all of Rn. Here we have our map A, also on all of Rn. Okay, here we have the conjugacy H, and this conjugacy must map 0 to 0, right? And so it maps some kind of neighborhood here to some neighborhood here, and because this is a conjugacy, it's a conjugacy on these neighborhoods, okay? Or at least, as I said before, you just have to be a little bit careful because these neighborhoods are not invariant, so it's a local topological conjugacy in the sense that I said before, as long as the orbits stay in here, then you have the conjugacy on those set of orbits. Okay? Yeah? So this is just a little kind of, you know, basic corollary.
We can also say because of this condition is satisfied over M, we can prove easily using triangle equality that it is satisfied over the closure of M. Okay?
Yes,
and using this, we restrict the functions to the closure of N, because in closure now would be a closed subset of Rn, it will itself be a Banach space, and we use the
no, it's not a Banach space if it's a closed, because it's not a vector space, right? I mean, it's not. If it's a bounded region, then it's not a vector space. This is a bounded neighborhood of the origin.
Yeah.
Right? And also that becomes complicated for the dynamics, because the dynamics must map outside. So it gets complicated if you try. Of course, it's essentially the same thing. But the formally correct way is easiest just to say, okay, you define our new function which satisfies the assumptions of the theorem because it satisfies this everywhere, okay? There you apply the conjugacy, and therefore that conjugacy is a local conjugacy on this neighborhood. Okay, so before we prove the proposition 1, how do we now prove with proposition 1 and 2, how do we prove the Gorman-Hartmann theorem? So let's remember what we want to show. So we have yes?
Because if it is hyperbolic, then now all the eigenvalues are in the unit sector.
Exactly.
And therefore, by proposition 1, we can change the norm to make it contraction map. And therefore, by proposition 2, we get that the function itself and its derivative would be topologically.
But how do we get this condition here? That's the only, you're right. So yeah, so that's basically the argument. So let's write. Okay, so we have our map F from Rn to Rn. Okay, we have f of p equals P. So we have a fixed point. Here we have A equals to df of P. Okay, so here we have our linear map, and here we have P, our fixed point. Yeah? Now, since we are in our N, let's assume, to simplify, that this fixed point is at 0. We can do that, okay? Because we can just take, instead of f, we can take f minus f of p. We can just translate the whole thing, so it's easier, okay? So assume without loss of generality, assume without loss of generality that p is equal to 0. It's just a little bit easier to do this, okay? So here we have our nonlinear map. This is 0. This is 0. We have our two fixed points. So yes, so we can take a norm on A, for which this is contracting. So by assumption of the Goldman-Hartmann theorem, we've had that all the eigenvalues are inside the unit circle. By proposition 1, this implies that there's a norm on Rn such that this is contracting. Let's assume that we already have this norm. Okay, so let's just write it like this, A less than 1. Okay, and we would like to show that these are locally, that these are locally topologically conjugate, right? Because that's what we're trying to prove, local linearization. So we're trying to prove that there exists some neighborhood here, and there exists some neighborhood here, such that these are topologically conjugate on these neighborhoods. Okay, so as you said, so we've used the first one to say that we can apply proposition 1, and because the norm is less than 1, we can apply proposition 2. But what does proposition 2 say? Proposition 2 says that we have a linear map, which is this A, and we have a nonlinear map, okay? And this nonlinear map needs to satisfy this condition here. How do we know that our nonlinear map satisfies this condition here? It's differentiable, and so?
The difference. I think we should use the definition of the derivative.
Yes, so since f C1, okay, in a neighborhood, so so we can write it, let me just see how I look here. Let delta f is equal to f minus df of 0. Right? So we have the derivative. We have this map f from Rn to Rn. We can just write the f, which means, okay, which is equal to f minus a. Okay, so this means that f is equal to a plus delta f. So in other words, we can write f as the linear map A plus something, some delta f. Okay? Now, since it's, what is the derivative? Notice that, so since f is C1, then delta f is also C1. Right? Because f is equal to a linear map, which is C1 plus delta f. So delta f is also C1. So what is the derivative at 0 of delta f? And also the 0 is a fixed point for delta f, right? Because 0 is a fixed point for f, 0 is a fixed point for a, so 0 has to be a fixed point for delta f. So delta f of 0 equals 0. Okay? And what is the derivative? Let me get some more space here. Well, let me write here. So the derivative at 0 of delta f is equal to, so delta f is equal to f minus df of 0. So this is equal to the derivative of f at 0 minus the derivative of df 0. What is the derivative of df of 0 at 0? Is this it itself, right? So that this is a linear map. Its derivative 0 is just the linear map itself. Okay, so this is just df of 0. So this is just equal to 0. Okay, just a small calculation, but it's not completely intuitive. So what we're saying is that when you write, it's a bit like the Taylor expansion, essentially, right? So we write f as its linear part plus a nonlinear part, right? And this nonlinear part does not have a linear part. It's exactly the nonlinear part. So its derivative is 0 because it does not have a linear part in some sense. Okay, it's a strictly nonlinear part. So this has a nonlinear part, so the derivative of this is 0. So what is the Lipschitz constant? What is the Lipschitz constant of delta f? What is the Lipschitz constant of delta f at 0, near 0? So the derivative is 0, and it varies continuously because it's C1, delta f is C1. So it means that the derivative in a neighborhood of 0 will be close to 0. Okay? In particular, it will be small. Okay, so for any epsilon, so for all epsilon greater than 0, there exists a neighborhood n, okay, such that dx of delta f is less than epsilon, okay, and therefore, well, it doesn't matter, and so the Lipschitz constant of delta f is less than epsilon. Okay, so for epsilon sufficiently small, we can get that. So for epsilon less than minimum between a minus 1 minus 1 minus a, okay, we get the result. Okay, we get the assumptions of proposition 2 are satisfied. Okay, and therefore this says that A and F are locally topologically conjugate. In our particular case, in some neighborhood, A is the derivative of F at the fixed point. So these conclusions of this imply that this here, there's a neighborhood of 0 for F in which the dynamics is topologically conjugate to the linear part A of F in some neighborhood. So the moral of the story is really just simply that here we are putting a condition on the Lipschitz constant of this perturbation, okay? And if this is, if you're looking in the neighborhood of some fixed point and A is the derivative at that fixed point, then as long as your neighborhood is sufficiently small, you can make delta F as small as you want, the Lipschitz constant. Exactly because of this fact here, because the derivative at 0 is equal to 0 because it's the nonlinear part. Okay, this completes the proof of the Glogman-Hartmann theorem in the case in which the eigenvalues are inside the unit circle, assuming propositions 1 and 2. Proposition 2, we've seen, follows almost immediately from the main theorem. Proposition 1 I'm going to do now in the last 15 minutes. It's just a straightforward calculation. Let's see. Any questions? Questions?
Maybe.
Go ahead.
No, I was thinking of the case in which the eigenvalues are at least one is outside the infinity. So
Yeah.
what we should do? We have to look at the real part or something. The eigenvalues are also complex.
Yeah, in that case, you will see we will prove this part is all more or less exactly the same. But the main theorem about the conjugacy, if you can divide your space into one subspace which is contracting and another one which is expanding, we will see the way we construct the conjugacy there is that you split that construction in two parts in which you construct it along the contracting eigenspace, and then you look at kind of the inverse map you take the inverse in the expanding eigenspace. And you construct it in two ways, a little bit like we use the fundamental domains in 2 dimensions by taking the fundamental domain inside one eigenspace, the fundamental domain inside the other eigenspace.
That's what is called the stable manifold or something. There's like a term that says that you are talking about the decomposition of this space.
Yes,
So
when we have a saddle,
yes.
right? When we have a saddle point, then we have one eigenspace that's contracting, that's sometimes called the stable eigenspace, and one that is repelling, that's sometimes called the unstable because points are moving away. And using the local topological conjugacy, as we saw at the beginning, we have the nonlinear, around the fixed point, we have nonlinear versions, maps of those eigenspaces, and those are sometimes called the stable manifold and the unstable manifold. They're just the images of the stable and unstable eigenspaces by this conjugacy. That's all they are, okay? Although this conjugacy just gives you that these are continuous because this is a homeomorphism topological conjugacy, so it tells you that these curves are continuous curves. But doing more work, you can show that they're differentiable curves. Okay, that's a slightly different structure. But anyway, let's prove proposition 1 now about the norm. This is again a simple case of a calculation which is done in more general case. It's quite an important calculation. It's done also in a more general setting. So we'll do it in this case because it's much more useful to have a contracting norm than just one looking at the eigenvalues. So how do we prove this? So proof of proposition 1. So the first thing we do is we're going to take advantage of what we said before, which is we know that A is linearly conjugate, right? So A is linearly conjugate to B with B less than 1. Okay? This is just by linear algebra, as we said. You put A into its normal form, okay, diagonal form or complex normal form, so that it is actually contracting. So these, however, are two different. This is slightly different from saying that we change the norm so that A exists. Okay, this is a linear conjugacy. So we have that A. So A is linearly conjugate, so that exists a linear map P. Okay, such that A is equal to P B P minus 1. Okay, this is the linear conjugacy between the two. Now when you have a linear conjugacy, so I'm thinking of which picture would be more useful in this case. So we have, let's suppose we have the complex conjugate case, for example. So the point here is that we have, in the nonlinear case, in the non-contracting case, we might have something like this. But this is linear conjugate by P to something that looks like this. So because this is a linear conjugacy, then we can iterate it, right? So AN is equal to P BN P minus 1, okay? Because if the map is conjugate, then all the iterates are conjugate. You take iterates of here, they're still conjugate by the same map P, okay? And so if you take the norm of N is equal to the norm of P Bn P minus 1, and this is less than or equal to the product of the norms and this is less than or equal to,
I think there's an exponent of n.
sorry, yes, thank you. So what is the norm of Bn?
Is maximum lambda n model. I mean, if we take eight values.
Lambda?
Lambda, model lambda n.
Lambda to the power n, exactly, right? Because here we have this, we can write this is equal to lambda less than 1. Okay, the norm is a certain number. So lambda is positive because that's the norm, right? So we can write this as, and of course, if you iterate, this is lambda n, right? Because this is saying that you take any point and the norm of its image of the image of that vector will be strictly less than lambda. So you iterate again, it will be lambda n. Okay, so here the norm of Bn will be lambda to the n. Okay, where lambda is less than 1. Lambda is in 0. Okay, so we can write this as equal to C lambda n, where this constant C is just this product. So what this is saying is that even though the norm of An, so this already is interesting, okay, what this is saying. This is saying that the norm of A is not less than 1, okay, but just by using this conjugacy we can show that if we iterate, eventually this product, the norm of An is going to 0, right, because this is going to 0. This is going to 0 because lambda is less than 1, so C to the lambda n is going to 0. So even though the norm itself is not less than 1, so it might be that after one iteration, you see, so you have this point here, okay, and then you look at its image, this vector here is maybe getting bigger, right, and maybe it's getting bigger again, and then it's getting bigger again, and then it's getting bigger again, but after a while it starts getting smaller, and after a while it comes down to this, right? So after some number of iterates, this vector must get smaller, and then it must keep getting smaller. Okay, so this constant C is here to help you survive the first few iterates in some sense. Okay, whatever this constant C here, even if it's huge, it might be 1,000, eventually this lambda to the n is going to kill this constant here, and this whole thing is going to be small. And this picture is exactly that. Even though this may be huge, you might have to take 1,000 iterates before you start coming back and getting smaller. Eventually this, because you know that this is eventually going to 0, eventually this is going to be smaller, and it's going to be smaller at this rate. Okay, so this is the first observation. So if I'd written this as a lemma, I would just say this, that there exists a constant C such that for every n, An is less than C to the lambda to the n, and in this case, using the linear conjugacy, we have an exact formula for this constant C. And you see that it makes sense, right? Because this linear conjugacy is in some sense how much it's distorting. The norm of the linear conjugacy is taking this spiral here to something very stretched. So the bigger the norm of one of these, the more this is being distorted to something stretched, and so the bigger the constant C you might need to deal with this situation. So now, okay, so this shows that, so An is eventually contracting in some sense. Eventually means sooner or later now choose some lambda tilde strictly between lambda and 1 and n greater than 1 sufficiently large so that C lambda over lambda tilde to the power n minus 1 is less than 1. Is this possible, that there exists some n like this?
Yes, sure.
Okay.
Because lambda over lambda tilde is less than 1.
Exactly.
Therefore we can.
Exactly. Okay. So we will see why we have this in a second. So now we need to define the new norm. So let me write this here. So let define, if you take a vector, you define the norm v star of this vector to be equal to the sum from I equals 0 to n minus 1 of ai of v, let me just write it as this, a and b over lambda to the I. Lambda tilde. So. Okay, you just look at it like that, there's no reason why this should work, we're just going to show that it works, okay? But you can see this is a simply, because this n does not depend on v, this is just a fixed n, so we're just saying, take your vector v, iterate it big N times, okay? And take that as the norm of your vector v base, normalized by this lambda tilde I, okay? And then this gives a new norm. It's very easy to check that this is a new norm. This is not even an infinite sum. It's just a finite sum. It's easy to see that it gives a new norm. And now we want to check that. Let's look at the norm of AV and compare it to the norm of V star. We would like to show now that this is a contraction, right? So what we want to show is that AV star is strictly less than V star, okay, in this new norm. You really contract. So even though the picture continues to look like this, okay, so you have vectors, you know, you have, you may have a vector here, which maps to a vector here, okay, but I've changed the norm. I've changed the way I measure these vectors, okay? So now according to my measurement, according to this new norm, this is just, this vector is actually smaller than this vector here, in this norm, okay? A choice of a norm in Rn is really just a choice of a unit circle. I don't know if you've studied this, if you've done this, right? If you, sorry, an ellipse. When you define an ellipse in Rn, then it defines a norm by defining that ellipse to be a unit circle, and that defines a norm. Okay, that's a good way to think of norms in Rn. You take an ellipsoid and then you define that ellipsoid to be unit, okay, and that defines a new norm. This is essentially what this is doing. It's taking an ellipsoid and it's stretching it, so it's defining that to be unit. And so this will be equal to, by definition, so this is I equals 0 to n minus 1 of ai of AV, right, over lambda tilde I, okay, and then you do a series of steps. So this is of course equal to just I plus 1, okay, and then this I pull out some lambda tilde I, so I can write this as lambda tilde times the sum of a I plus 1 of v I equals 0 to n minus 1 times lambda tilde I plus 1. Okay, so I changed the index a little bit, so I put I plus 1 here, and that gives me an extra I which I pull out here. Okay, and then I write this as, so I separate this out into lambda tilde, the sum I equals 0 to n minus 1 of ai v over lambda tilde I, right? And then which parts am I missing? So that means that I am missing when I equals 0 here. So when I is equal to 0 here, I get I0 here, which is missing from this, so I need to subtract the case I equals 0. And the case I equals 0 here is just 1. This is just v, so this is lambda tilde v.
But excuse me, in the first case there is no index for 0. When I equals 0, we have the exponent is 1.
Exactly,
But
exactly.
here, if we put I equals 0, we get A0.
Which is v.
Ah, okay.
So I need to subtract it.
Yeah.
Exactly. So in this sum, I have a term that is not here.
Okay.
So that's why I subtract it, right? But we also are missing a term, which is we're missing the term when I equals n minus 1. This gives a n lambda tilde n. So this is missing from this sum, so I need to add it back in. So this is equal to lambda tilde times a n v over lambda tilde n. Okay, so this sum is exactly the same as this, because here we're missing this term and we've got this term extra, so we subtract this. Okay, and this now is exactly equal to the definition of v star. Right, so this is equal to lambda tilde v in the norm v star, okay, minus lambda tilde v plus a n v over lambda tilde n minus 1, okay.
Why n minus 1?
Excuse me?
The n minus 1 on the lambda. Okay, okay.
Yes, because there's an extra one here. But we have, so what we would like is basically this. We want to show that these do not, so this is subtract. We want to show that this is less than equal to this, right? Or less than equal to something strictly less than this. So lambda tilde is less than 1. This is not a problem because we are subtracting. So this is actually smaller. The only problem is this, okay, because we are adding. But by the assumption on n, so by assumptions, by the assumption on n, we have that a n v over lambda tilde n minus 1 is less than equal. So what was our assumption? Remember that a n v was less than equal to c lambda over lambda tilde to the n minus 1, right? Yes, times v over lambda tilde n minus 1. Is that right? Yes. So this is equal to, where this is So this is lambda tilde minus n minus 1, which cancel this. So this is equal to C lambda, wait. So so the assumption was that C lambda, wait, I forgot what I wrote on the assumptions.
Because we have just made some computations. We have seen the norm,
Should
the
be
power
lambda.
of n is less than C times lambda power n away.
Sorry, wait, so,
Maybe
sorry, so yes, I missed one step here. So what I meant to write is that this, yes, sorry. What I meant to write is, you're right, so that this is C lambda n V, right? And this maybe should be n or no, lambda n?
You're right.
Yes, and so this now, the assumption on lambda tilde and C is that this is equal to C lambda n minus 1 over lambda n minus 1 times lambda V, and this is less than 1, and so this is less than equal to lambda V. Right?
Yes.
There should be lambda tilde because we have lambda tilde.
Lambda tilde.
And we can write n, just n, not n minus 1, just n and lambda tilde again.
It's okay.
No, we have lambda tilde, so we need lambda tilde and we can write lambda n over lambda tilde n and lambda tilde again.
Yes, so we want, because we don't want this, so wait, this is okay, right? C lambda n V over lambda tilde n minus 1, right? And then now here, we,
That's okay. For me, calculate here.
Anyway, we have lambda less than lambda tilde.
we have lambda less than lambda tilde, exactly. Yes, exactly. No, lambda, yes, because lambda tilde, this is less than equal to lambda tilde V.
In fact, we're choosing n such that C lambda over lambda tilde to the power n minus 1 is less than 1. So we have all of this is less than 1, and at the end we get lambda norm V.
Yes, but I'm thinking there's still something missing here because we would like, because it cancels with this.
Exactly, and that's all.
It cancels with this, exactly. Yes.
No, but we will get lambda, not lambda tilde.
It doesn't matter.
Lambda less than lambda tilde.
Lambda is less than lambda tilde. Yeah, so it doesn't matter. If we put lambda here, it cancels with this. Okay? And so this is less than equal to lambda tilde. This time. Yes.
Do we assume that A is invertible?
Yes, I'm always assuming it's invertible, although I'm not sure that it is. In some calculations, it's not
It's
necessary.
necessarily in the point to show that this is in fact a norm, in that if the norm of V, if V is equal 0, we need to prove that V itself is 0. So we will conclude that the norm of AI V equals 0 for every I. And therefore AI V itself equals 0, but now we need that A itself to be invertible to conclude that V itself is 0, or at least injective.
I'm not sure that that's necessary. Maybe. We're only looking at this invertible cases anyway, but I'm not sure that that's necessary for this specific calculation.
Not for the calculation, but
For here.
Yes. to
Yes,
prove
yes,
that,
yes, you're right, yes. 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 Okay, so this is the adapted norm. This is sometimes called the adapted norm. So all the norms on Rn are equivalent, so it really doesn't matter. So this is another way again to say that you know, you can, even if the picture looks like this, you can work with it, with the adapted norm as though it was contracting this whole situation. Okay. Okay. So next week we will do the proof of that main theorem, which involves constructing this topological conjugate. Okay, these were just all corollaries of this.